This is a test, and yep, okay, timer's going. Okay. Explain to me what this does. Explain it to me like I'm 10, like I'm a dog. What does it do?
What is this? Okay, now, the computers on the control system are all, and they're running a specially written for labs and research control system, EDM, and it's configurable. It's not hard to go in and edit the appearance and location of anything. With this particular screen, though, I've never cared for how it was laid out, but I don't have a better idea. The way that the tandem works, here's kind of this odd little drawing that was just in terms of orientations of things, but it's you go up one side and come down the other. The way this control screen has always worked is you go down this side and then you go down this side, and it's always bugged me that it's not particularly anatomically correct, because it seems like you should be going up this side and down this side, and a few people have tried over the years, but it's never really worked that well. But this section here is the stable injector, the ICES injector for stable ion species. Now, you have...
Not the Islamic militant group.
No. You have various things in here like ES is electrostatic steer. It's using high voltage to nudge the beam one way or other. And then you have EQs, are electrostatic quadrupoles, and that's it's a focusing element, but you have to have them in pairs at a minimum due to the way they work, because they can only focus on one axis, but they'll defocus on the other. So you have to use two of them
In order to get both.
Mm-hmm.
Okay.
Or sometimes they'll do 3, and then the first and third one do the same thing, and each are only doing it about half as strong as the center one is.
What's the point of that?
It gives you a more symmetrical shape. In
Oh,
terms
okay.
of if you started with a circular beam and you just did a doublet, 2 sections, you won't end up with a circular beam. Whereas if you do it with a triplet, 3 sections,
You have...
you can do.
Okay.
You'd have to talk to a real physicist to find out the particulars on that. Usually the first and third sections are slaved together, and each individual run is running about half what the center is. I can show you on paper how the focusing works. We'll get to that later. Okay. FC is a Faraday cup. It is just something you can hit and measure beam on. Now, when you're trying to measure beam, you can run into an issue. I mean, basically, an ion beam hits this thing, and you basically just measure how much current is hitting this. However, in some cases, if you're hitting it too energetically, you can knock electrons off of it, which can hit nearby things, and it can make it look like it's a different amount of beam. Okay, like if you hit with a positive beam, one proton hits or one positive ion hits,
Okay.
one electron's going to flow up through ground, through all the current monitoring to even it out.
Okay.
Okay, so a million hit, a million come in. Should be 1 to 1. However, if I hit with 10 and I knock one electron loose and it hits ground, 11 have to flow through. So, at a million hit, then that's 1 million, 100, or, at that scale, 100,000 electrons fly off and just, hit the chamber or whatever, reach ground. 1.1 million has to come up through ground and be registered as current. It's inflating the amount that you have. So like with a negative ion, the electrons are going to flow back through ground. However, if you hit and knock electrons loose and they go flying wherever, not as many have to go to ground.
And I see on here it says, I guess that's what the yellow is. Where is it? Yeah.
What are you trying to find?
Those things there.
What's that?
I guess those are the electrons, the negative one.
This would be a current reading. And different ones have different instruments on them. Some of them will go down to the picoamp range, -12. A few of them will go one more lower, like -13 range. We're dealing with a lot of cases very low levels of beam. Now coming out of the stable injector.
So wait, so is that then like a log scale then?
Yeah, it's
Okay. So -1 is...
well, this is the actual, number on the current, and then this is the exponent. Scientific notation.
Oh, duh. We're in a lab.
Yeah. And then you can also assign to a meter, because when you're trying to tune stuff, an analog meter is easier to tell, is the beam actually, going up? Am I accomplishing something by trying to tune it? So, any of these, like the steers or the quads, you have these little sliders which will control where something is. It can be just an annoying way to do things, though. Sometimes it's nice just to be able to click on here. But what you can do is actually assign what's here. By, click on the button, and presto, now it's something else entirely that's assigned there. And you're only tuning a couple things at a time. So, you got 3 knobs. This one is usually just going to be your major bending element. That's bending magnet 13.1. And what it does is you basically have ion soup coming out of the stable injector. What that is set up for is everything that comes out is going to have a -1 charge. So from there, the only thing that's going to be different about them is the mass. They're all going to have the same energy. The platform sits at, all told, about 200,000 volts. So everything is coming off of there at 200 keV, kilo electron volts. I don't know if you're familiar with the unit.
Somewhat.
Yeah, okay, 1 electron volt is the energy an electron gains going across a 1 volt gap.
Sounds somewhat familiar from physics, but
Okay.
it's been a while.
I set up a voltage gap and send an electron across it. If it's a 1 volt gap, it gains 1 electron volt. If it's 5 volts, it gains 5 electron volts.
So this is kilo electron volts?
Yeah.
So thousands.
Yeah,
Okay.
so it's at 200,000. And it's a couple of steps. You've got, like this is at, the platform's at 180,000 volts, and then you've got about 18,000 volts for, the acceleration voltage, and then the cathode's at another 2,000 volts. So you're just kind of handing it off, but by the time it leaves, it's at 200,000 volts. So at that point, everything coming out of there is a -1 charge and has 200,000 volts of energy. So what's going to matter, though, is you send it through this magnet. What that can separate it out on is its mass. So So this thing is set up, and I'd have to turn on water systems in order to turn this on and show you, but it will have a mass indicated here. Wherever it is. There is mass. And usually that's what you're aiming for. You'll put a cathode tip in this thing that is filled with a specific type, of a specific element, a specific, maybe an enriched isotope of an element, but usually just the naturally occurring, it could be anything. We might be doing an oxygen beam, we might be just doing protons, fluorine, calcium, copper, nickel, who knows. But that's where the chart of the nuclides can come in, because you have isotopic abundance of all your isotopes. And then we're talking just the stable ones now. So if you want to go look at that.
Away. Oh.
Okay, this is the chart of the nuclides. Now, any particular element goes across. These are all tin. And there are various isotopes of tin. The important ones here is just what's gray. Because the gray ones are the ones that are stable, if I've got my info right here. Yeah, so what you'll see is a number underneath each isotope symbol. And that is the percentage of the isotope that is that atomic weight, that mass. So tin 122, 4.63%. 124, 5.79. 120, 32.58. 118, 24.22. So, if you have natural tin, I mean, you've got a little of this, a little of this, a little of this, a lot more of this and this, a little of that, a little of that. If you're after a specific thing, though, you've just got tin, and you'll have some copper, because copper's in there, and whatever else is along. A little bit of air leaking in is inevitable in any vacuum system, and it is under vacuum. So a little bit of nitrogen, a little bit of oxygen, soup. But if we're just after, we're just after tin 124. Well, you set the mass to 124, and then only things that are 124 are really going to be able to get through. Now, you're not likely, unless you were intentionally trying, you're not going to have palladium or silver or cadmium or indium, antimony. None of this stuff is likely to be in there. So this should be the only thing in there that's at 124 that's going to be able to make the bend up that magnet with the magnet set for a mass of 124. Understand how that works?
I think so, yeah.
Okay. Now, as a caveat to that, it is possible to have a molecule come out of the stable injector.
So what do you do if that happens?
Well, you just have to be aware of it. A lot of times what you have to do for it is planning.
And how rare is something like that?
It's not really particularly that rare. It doesn't necessarily, later on, you'll see why it isn't too important, but it can be, because if you run into something, let's see, I guess it's a matter of if there'd be anything at a mass of 62. Half that. Well, probably not copper. Nickel 62. If you
Wait.
manage,
Why not copper?
because copper 62 has a
Oh.
9.74 minute half-life. It wouldn't be there. You're assuming that after 10 half-lives, it's gone.
Okay.
So unless you put it in and we're running within 90 minutes, it ain't there. At any rate, though, you could have two nickels stuck together, and you'd have to talk to a chemist whether that's a thing that can happen or not.
Usually it's called dimes.
Hmm?
Usually they call it dimes. Sorry.
Okay, but it's for purposes of this analogy, we'll just go with, that it's possible for two nickel atoms to stick together. They would have a mass of 124. That magnet is not selective enough to tell them apart. There are magnets that
They
are.
can-
I
they
can
can?
show you
Okay.
one. Yes.
This one isn't.
No, it's not meant for it. It doesn't need to be. But, okay, so we've bent this thing and it's going straight up now.
Okay.
And at that point, you go through various steering and focusing elements, and it's looking at the voltage up in the terminal. So it's straight up, faster all the way, and it's... We'll get to that later. At any rate, once you get up to the top, you've brought a negative ion, attracted it to a high positive voltage. You have to get it back out, so you need to turn it into a positive voltage. You do that with a ridiculously thin carbon foil. This is basically done. You deposit the carbon on a glass slide to make this foil. You can either do it with vapor deposition, or you can drop, a colloidal solution of graphite onto the slide, float it off in water, scoop it out with a fork, a little frame fork thing that it will be on, or depending on the thickness of the foil. Most of the ones here are insanely thin, and it's kind of on a, it's on a little circle. Dry it, and then you load them into a carousel, because these things aren't going to last forever. I mean, these things are, most of them are 5 to 10 micrograms per square centimeter. 1 microgram is like 25 atoms thick. You're not talking a lot of material there. It is insanely fragile. But
How do you keep from breaking it? Like something like that.
you can't jar it. You can move it around, but yeah, I've seen thicker ones that, back where I used to work, we would use, one machine used 75 microgram per centimeter squared, which is, that's thicker, but it's still, if you went, it was gone. It's not strong enough to stand up to that. Another one is using like 200 to 400 micrograms. But we've got a carousel with a whole bunch of them on it, so if they, start wearing out, we can advance and put a different one in.
Is there an advantage to, because you named like 3 different thicknesses there. Is there an advantage to using one over the other?
It depends on your application.
So it's not all using this for the same purpose.
No, here we're basically using these, 5 to 10 microgram ones. And if you get too thick, you start affecting the energy of the beam. You will slow it down, and that can throw things off. You can, you're aiming for, not over stripping, basically. You're not going to get everything. What you're doing is stripping electrons. So, if you're dealing with a proton, it's going up with 2 electrons, and you just want to strip them both off. That's simple. If you're dealing with something like tin, which is number 50, which means it's going up with 51 electrons, you are not reasonably going to strip all of them. It would be very difficult to control this thing if you did. What you're after is to strip, 5 or 10 of them. There's a program that will predict and say, if you go up with this isotope and the terminal voltage is this and it's moving this fast, this is your, what percentage of it is going to have this charge state, this percentage is going to have this charge state. So from that standpoint, you have to look at, what's going to be the best as far as giving you the most beam to work with. But there's other considerations as well, because you need your terminal voltage high enough to regulate, but not so high that you're likely going to be sparking out all the time. And if you are running up, like I said, this thing's rated for 25 million volts. If you're running that high, you do have the possibility that it's going to spark against the tank, or just something. It could spark inside the tubes, on the outside of the tubes, because it's not. It's not a long, just insulated tube top to bottom. You have all of these little ring sections. You have metal rings and ceramic spacers, and it is a whole big long stack of those.
So that's basically if a spark did happen, it couldn't just go all the way through. The ceramic stops it.
It's not going to really go, just all the way top to bottom. What you're likely going to have is terminal to tank. Terminal's where it's highest. It's just, you've got a bunch of resistors, so you have this big voltage divider going all the way down to the bottom. So, you've got all of these sections in there with all of these, with the kind of voltage divider tubes, basically, with a resistor across everything. So you've got a gradient that's set up. So tube section to tube section isn't that big of a voltage difference. It isn't as likely to spark there, but the terminal is just this big metal sort of a sphere, and that's, it sticks out a little further than just the body of it does, so it's a little closer to the walls of the tank. So the likely spark there, if that happens, that's pretty much all your voltage goes instantly. So the higher you're running on voltage, the more likely that is to happen. Another thing, and something that we'll have to deal with, because they want to run here, I think in March, so in February, we have to do is called conditioning, and that's where you basically clean up the segments a little at a time by, you short out most of them except the segment you're working on, bring it up to high voltage and basically let it
May
spark
I
itself
have your
clean.
attention, please?
So, at any rate, back to the original point though, you've sent it up, you've stripped electrons off, you've got a certain charge state, that you've decided to work with. There's a magnet at the top that you set up, and you can really only pick one charge state to work with. Now, this can be where the whole nickel thing comes in. Because if you pick an even charge state on this tin, say you picked, a charge state of +6. If you have a double nickel going up, and it strips, a nickel 62 with a +3 charge state is going to look very similar to a tin 124 +6 charge state. The magnet won't be able to tell them apart. So you could have both of them making that curve and coming down.
So how does that alter the final product?
It shouldn't, but it can confuse you because you've got all this beam here, and then you get past. There's one more big magnet right after leaving the tandem that it's pretty much the, I guess, final say in what actually gets out. And if that's set correctly, then only the right one will. The tin shouldn't be able to make it past that.
And
Or
if
the
it-
nickel rather, the tin will, the nickel won't. But it's kind of a matter of, you know, making sure it's not there to begin with is good, because you might make it through. However, if you pick a +5 or a +7 charge state, there is no charge state for the nickel that's going to make it look like that, because it would have to be half. You would have to have 2.5 or 3.5.
So do they do that on purpose at all to pick elements that are an odd number charge so that nothing can be confused with it?
Yes,
Okay.
that is sometimes and frequently intentionally done. You have to think it's called an analog beam in terms of it's analogous to it,
Okay.
numerically speaking. So you're
Practically the same thing.
Huh?
They're all just little whirling balls of energy.
So yeah, you've got, you know, the final magnet down at the bottom there, but wherever I was now.
Odd
Yeah,
number.
You do have to think in those terms, making sure you're not going to have something else along. I mean, some of these, you know, particularly you get up into heavier stuff, the odds of you having any of that lighter one there at all, other than copper, because the cathode tips themselves that the isotope's packed into, it's a little rod of copper with a hollow part at the end. You take a powder, kind of pour it in there, and then tamp it down with, you know, a hammer and a punch. So if you didn't put it in there, you know, having tin, sure, fine. Having nickel along for the ride is unlikely. But once you get into lighter things, you know, you might have things that are a little more likely to be along. You know, like I mean, if you're working, say, with sulfur at 32, well, oxygen will be there. Oxygen is always there.
Always.
Likewise, silicone, 28. I don't know if you can even do anything with that. Nitrogen's at 14. Nitrogen will always be there. Probably more nitrogen than oxygen. Funny how that works. Again, nature reports a vacuum. There is no perfectly sealed vacuum system that will not have air molecules finding their way in. It just doesn't happen.
So it's not just a matter of we don't have the money to make it, it won't happen.
Well, someone might have the money to make it, but as far as in most applications, you have vacuum pumps to try and pump it out at least as fast as it leaks in. And from there, it's, you know, the vacuum you can get down to is going to depend on, you know, how good your vacuum pump is, how tight your system is. But if you shut off the vacuum pump, it will slowly work its way up to atmosphere. It might take a long time,
But it'll get there.
yes, or it might be there really quick. So, but we can worry about vacuum pumps later. At any rate, now that, you know, you've stripped it and turned it around, and once again, BMT1, that's the big magnet at the top that, you know, bends it and points it back down. Now it's at a positive charge, the terminal's at a positive charge, and it's just going to be repelled by that. So, and at that point, say that just in terms of simple math, if we started with 10 million volts on the terminal, we sent the stuff in with a -1 charge, it's going to have 10 million electron volts when it makes it to the terminal. Now, usually you put it down just a little because it's already starting with 200,000. So, yeah, but we'll just go with simple math. We're at 10 MeV at the top. If we went for a charge state fraction of 5, turn it around, send it back down, we're going to add on another 50 MeV. So a total of 60 MeV.
Okay.
So now, electron volts is a unit of energy. So it's not necessarily, it's not directly corresponding to speed, because energy is 1/2 mass times velocity squared. So as your energy goes up, your velocity is not quite going up. It's at that point, since it's a square function, but it's energy to velocity, so velocity goes up linearly, energy goes up, it's a square function, so it's the other way around. If energy is going up linearly, velocity is going up over the square root function.
Okay.
So, they're coming out, we have this particular isotope, it's this mass, it's this energy, it's this charge state, and we have a little program that tells us this final magnet needs to be set for this particular magnetic strength. And this is one that's measured very, very exactly and precisely and accurately. You've ever heard of an MRI, magnetic resonance imaging? The actual name is nuclear magnetic resonance. We just dropped the nuclear because it doesn't play well as far as anything that you're using on the public.
Kind of got a stigma.
Now it has.
It'll give you superpowers.
Yeah. At any rate, there is a little sensor inside this magnet that's measuring the magnetic field. And what we're looking for, we have a regular little Hall probe on there as well, which will tell us, roughly where we are. The NMR number is the one we're trying to match. And basically, it's you wind up adjusting it. And on this little oscope here, that's stuck back in there, you'll see those two little peaks kind of going by right now. That's just basically noise. But when you have it in the right place, those peaks are basically together, and you can move them across the screen by adjusting the magnet, and you want it right dead center. And that tells you your magnet is adjusted correctly for what you're trying to get out of the machine. So along the way, you still have more steering and focusing things. Going up, you have, anything with a number, you're in a beam line. This is in beam line 13, this is in beam line 11. CD is column base. That is at the very bottom of the machine before you've actually started doing any accelerating at all. D2, these are, and that's they're sections of the terminal. D2, it's what you have is a dead section. Now D2 and D4 are bigger ones. 1, 3, and 5 are very small ones, but D2 and D4 actually have some things in them. Like in this case, you've got quads and steers, and then also another Faraday cup. And then likewise over in D4, you've got a Faraday cup. You also have another set of coil strippers. So as far as
taking beam up and steering it and focusing it as you go. Funny thing about a bunch of ions that all have the same polarity of charge on them, they have no interest in being with each other. So even if you got everybody parallel and straight and going, they're not going to stay that way. So you have to periodically nudge them back in. And then, likewise, you are going a fairly long distance down what you hope is a straight pipe. Occasionally, yeah, you have to adjust
For in
the direction that you're going. So here on the lower energy side, before you've really done anything, and likewise up here a bit, you can use electrostatic steering and focusing. Now when you start coming back down, you really don't have anything between the terminal and then when you get out here, and then this is beamline 16, and now suddenly the E's have become M's, and that stands for magnetic.
Maxwell's laws hold true.
So you have magnetic quads and magnetic steers, and I mean that's kind of a different thing.
Don't listen to him, he's lying. He doesn't know anything about this stuff right here.
This is Scotty.
He comes in every day and he looks at that screen, and I have to explain it all to him.
At any rate, now that we're at higher energy, you have to go to magnetic for all the steering and focusing. And then, the actual magnet to steer it, because right now we're coming straight down, and you have to move it so it's going horizontal. That one is a big magnet, and it's a very, accurate, precise magnet. You have, the little blip on the oscope telling you, okay, it's exactly correct. So you bring the beam out, and from there, it's probably easier to take you out and show you there. Okay, we call this the magnet room, mainly because of that magnet.
Good name.
Yeah. Now this whole beam line can be rotated to go to any of these lines that you see. Yes, it's standard to wrap foil on them just to keep them fresh. Keep things out, and it's a clean material. So down at the end, that blue pedestal there's an air line going to it, and it's kind of like, you float it on air. So while it's not, one finger move, but you can push it and rotate it around on this. We've got a few more lines over there. So, after we've got it, we've got it lined up, actually attached. Well, it's not attached right now, but there'll be a little bellows piece that bridges these together. This will go in between there, get clamped in place, all pumped down. We'll bring in, these carts over here, a couple of them are just for pumping things down, and then a couple of them are what are called helium leak detectors. More on that later. But we'll pump down the section, open these two valves, make sure all the valves in line are open. We run into that going down this line all the time. The experimenters have their equipment in the next room. We'll be trying to deliver them beam, and we're not getting anything out there. We'll ask them, are you sure all your valves are open? Oh yeah. And then we go look, and there's a closed valve. Every time! Now, earlier I mentioned vacuum pumps. This is a vacuum pump. It's basically a small jet engine. You have a lot of these little, you know, turbine fan blades going there that you're just using as a fan to beat the air molecules out the back end. And then you have what's called a roughing pump. It's a low-level vacuum pump, basically, or, you know, a rough vacuum pump. Right now, let's see, this line is in the -8 torr range. And you have to have either a turbo pump, you know, or a cryo pump on any kind of line that's likely to have a significant amount of leaks. But a turbo pump can only bridge you from, you know, it can't get it from high vacuum to atmosphere. It will get you from high vacuum to rough vacuum, -2, -3 range. That'll get you the rest of the way. So that kind of pump has to have a vacuum pump for it. At any rate, though, there's other various. I mean, this is a small bending magnet. It's not a straight line going into this beam line like most of the others. So you have to have a little directional tweak there. This is a steering magnet, but this is a weaker steering magnet. It'll give you, I mean, I don't know what the specs are on this, but a similar one I've worked with could adjust the beam about 6 milliradians.
Small.
Yeah, but you go a distance, that means a lot. This brown and silver box here, this is an ion pump. What you basically do, any stray air molecules that wind up in there get ionized and then implanted in titanium. And in most cases it'll chemically react and, you know, be trapped. In other cases, the idea is to just kind of implant it there and then coat it over. So it can get down to a very low vacuum. It doesn't need a vacuum pump, but it can't handle a heavy gas load though. Let's see what else we got here. We have this odd tape drive thing. Can't really tell so much from underneath, but it's basically, let's see, how much am I going to see here? It's kind of dusty, so I don't know how much you'd really be able to see. I mean, you can look at it if you'd like, but the top is dusty, but it's basically a big long tape. You take the tape, put it in the path of the beam, and then bring it back out and see what you got. This guy, I believe, is a electrostatic quadrupole box section, whatever you want to call it, which you can't really tell too much from the outside. Now, this is coming from the IRIS platform, the radioactive ion beam platform. So coming in here, you can either bend it and send it up into the tandem, or you can send it straight across. There's not really much there right now. This is a low energy radioactive ion beam, research target, whatever. And it's just for the non-accelerated, straight off the platform. If you don't need to bombard something with it, but you're just trying to actually, collect that particular isotope for whatever reason. Sometimes they're still trying to learn little details about some isotopes. Other times they're trying to run this into this and see what happens. Or, even make a new isotope. I think they've packed it up and taken it other places now, but there used to be a big detector array around this. And you've got various instrumentation things they have set up. And cables. Oh my God, do we have cables? One of the things we have, if you move the beam line, you've got these big switches. Now, this one doesn't get switched too much anymore, but when you move the beam line, you're basically using a lot of the same power supplies to control downstream elements. You're switching them with these boxes. So right now I'm on beam line 41. DRS, everything needs to be switched for that, so that the few standard elements in the next room will respond correctly. I adjust it in the control room. That magnet is what actually happens. I move it over here to 31. Well, I have to flip the switches for 30 to 31 so everything works right. Once upon a time, beam used to go from the tandem into the cyclotron, and this was one of the magnets that made that happen and send it off that way. They stopped doing that some years back. They switched about 20 years ago from being a heavy ion research facility to being a radioactive ion beam facility, and they reconfigured everything.
What's the difference? Which aren't a lot of...
Heavy ion facility, it was all stable.
Okay.
That are long-lived, that, you could actually get into the injector.
Okay.
Radioactive ion beam, you're actually bombarding a uranium target, making it undergo fission, and you're producing a whole lot of things. And you're trying to selectively grab out that one isotope of that specific element to accelerate that. And a lot of these, you have just the faintest wisp. They're just, just a few of them. This is the Darsbury Recoil Separator, DRS. Here's the display poster. And reading that, you'll know about it as much of what they do in here as I do. So.
Oh, we don't know anything about it, but...
Well, I can show you. This is basically the convoluted mess that most of the research, experiment rooms, whatever you want to call them, this is what they are. You have a tangle of equipment all over the place. The actual beam line comes in over there. Looks like they're set up. There's a bunch of detectors there, so I don't think they're going any further than that. But you've got large, steers and focusing elements going through here, and instrumentation.
Instrumentation.
Yeah. So as far as now, this is a quadrupole doublet, and I can draw out how that works for you later on. That's why there's coils on the 45s.
I'm guessing it's quad because of the 4 things in the circle
quadrupole.
And then a doublet is because there's two of them.
There's two. One individually is a singlet, but you always, pretty much either have to have a doublet or a triplet. But yeah, you look in here, you'll see 4 poles sticking in. So that's quadrupole. Here they've set up some array of detectors. Specifically what they're doing, couldn't tell you. But this goes on, you've got basically another quadrupole triplet here. These tan things here, the 3 of them.
If you ever thought science was organized, you were wrong.
Well, no, it is not. Remember, quadrupole with a U, not with an A. This is probably the second biggest experiment beamline. There is a bigger one.
In the lab? Or?
Yeah, on the other
Okay.
side of the building. We'll get there shortly. And it has even more twisted, tangled cables. on it,
Oh,
so that they-
yay.
A lot of this stuff, you have to actually talk to a physicist. Second floor to the tower. I mean, if you want to turn here, this is how thick the door is. And that's actually, for accelerators, that's a fairly thin door, but this thing doesn't run the same level of current as like a regular cyclotron would. You have a bunch of power supplies down here, and then the beam lines actually pass through. So, this beam line is the low energy stuff going into the machine. And then on the other side over here, if you want to sneak through and point at it, this is the line that it's coming out of the machine. And that big bending magnet that, it has the magnetic resonance sensor on it to determine, that we have exactly the beam we want. That's that magnet there. Saw it earlier. Other than that, this is just a place you walk through. Have a bunch of cabinets, store spare parts here. Don't really have to get to them too much anymore. This beam line comes in from the stable injector. And then this is that BM13 mass analyzer. You'd set it up for a particular mass to go through. Then, likewise, this is the beam line that comes down from below. This pipe would be for if you were sending up, a radioactive ion beam, and you have to have this magnet off, and it has kind of a little adjuster supply to zero it out. Because otherwise the residual magnetism is going to send this beam kind of spinning off. So, we can go look at the stable injector later. Because this is actually a straight pipe, but they're doing a fisheye lens to get that. But this is some of those piping sections. You have, rings of metal and then rings of ceramic insulator. Now, this is the bottom of the tank. Now, this hatch, when opened, you run cables all the way on outside of the tank on the top, all the way down, hook onto this. And this is the central service platform. It's an elevator. you can, get to the inside of it. The guy in that picture, he had to ride this up to get in there. You can climb out on these castings, big aluminum rings, donuts, whatever. But all the equipment that's in there, that's how you would get to it to service it. This is another type of vacuum pump. It's called a cryo pump. That's what's making that odd cycling noise. It literally freezes out anything that's in there.
So what's the advantage of this one over the others?
It's clean. It pulls down very low. Between this one and a turbo pump, the only real downside to a turbo pump is if something happens and you get a big slug of air or anything in a turbo pump, it'll destroy it. Saw one time it tore itself loose from the bolts that held it on the machine, and it just shredded itself. It was just bits of metal everywhere. Whereas this guy, it has an associated compressor, so it's just compressing helium, not liquefying it, just compressing it, and then expanding the helium in order to cool it down. It operates maybe 10 or 20 degrees Kelvin. So just anything that's in there. The only thing you can't freeze out like hydrogen or helium, but it has this array of, basically carbon pieces that kind of create a trap, so that those molecules and atoms that won't freeze out, that they can, they could get trapped in there basically. They just kind of run around and run out of energy and stay there. Now the whole tank, the way, all the equipment that's in there, you have to cool it off somehow. The main way you do that, you could just have heat radiate off the tank itself to in the tower. You have air conditioning systems. The other way though, the SF6 gas, you have two pumps here behind this. They're turbo compressors. And they actually will pump it through the tank. You send it through a cooler, pump it up, bring it in the top, and then it'll come back out the bottom. So, again, you've got, this is a quadrupole set of steering magnets here. These are stronger steering magnets.
See much because of the lighting.
Yeah.
Much better.
So, at any rate, this green magnet goes with that other big green magnet. It's not used anymore. It was one to guide it out of the line a bit, so that other bigger magnet down on the first floor could bend it horizontal to send into the tandem. There's some of the SF6 stuff. There's 3 vacuum pumps basically over on the other side of the room if you want to see them.
Sure.
The whole system, you got a dust filter, an oil separator, try and keep the SF6 clean. There's a dryer out on the other row. But then likewise, the thing with these kind of pumps is you have to have oil to use them. And when you take a pump and you suck the air out of it, well, the pressure's lower there. You have a tendency of oil to backstream into the chamber, which can be bad depending on what you're doing. But you have things like this just to take the oil mist out of it. It's describe what's in it. Part charcoal filter, part steel wool.
I have newt to a frog.
You know, but this is mainly just for when you're transferring gas. We have a separate building with 3 tanks in it that you can pump it all out of here, condense it, and store it over there. You know, it's that way you can get into the tank. SF6 is a strong greenhouse gas. It's an asphyxiant. If all of this leaked out, it could cover about 17 acres. It's about 200,000 pounds of it. And this tank pretty much goes all the way to the top. The whole tower is in this tank. So up here we have kind of a, I mean, this is the old gas console. So when you're doing any over this is the old one here. When you're doing any kind of transferring the gas to storage or back into the tank, this is where it pretty much used to be done. They were trying to transition to a newer, you know, all computer controlled system. And they're kind of sort of still working on it, but since we don't really do that much with this anymore, it's not any real big priority. Now, over there it's more getting into the mechanical equipment room. There's like a dryer, and then over on the far left is the lead area, that equipment room.
Which I can't go in.
Yeah, and there's really not much to see, and it's, you know, I mean, you got like some pumps, some more switch gear, like see that whole wall there, that's all a bunch of breakers and switch gear, motor control centers. It's electrical distribution, and there's more of it in there, which doesn't look too different from that. There really isn't much to see in there. So, for now, it's the stairs. This particular hatch would be for if the tank was open, you have that one elevator going up the center. This you have another elevator that's a ring around the tandem itself that we have to rig up. We can get in and get on here. It's up to you if you wish to walk all around it. It doesn't change much.
Alright.
And you have on the end of it, it goes into the tank, and there are basically 6 or 7 needles on the end of the tank. And you push it, you run it in until it's drawing an arc, a very low level arc to the terminal. And then based on the distance and, you know, the amount of current going and all that, it helps regulate what the, you know, how your voltage goes, how high it is, where it is. Because if you start sending beam through it, I mean, if you're just letting it run free with nothing to regulate it, it would keep varying, which means the energy of your beam would keep varying. You have a couple of little odd spinning motor things that spin these little, almost look like a flat fan blade, and they kind of sense the electric fields in there and tell you what your voltage is. But it's kind of a not roundabout thing, because you have to successfully get a known beam through the machine to know for sure if it's really reading right. If it's not reading right and you're assuming it is, you'll never get that being true. Now that itself is not all of the tank. The tank's a little wider. Down.
Oh, alright.
You can see there. That's how far out the tank actually goes.
Ah, okay.
This section was pretty much built in order to lower things in. So this is how big the actual machine is. About that big around, a little smaller. These two spikes, those get lowered down all the way out the bottom and attached to the elevator, that central elevator. Where they put all the security cameras too. It's got a good view. Now, need to come up and do a panoramic shot from here sometime. So there's that traffic circle over there. Just for sake of reference. And this building with the corner sticking up,
Yeah.
that's the visitor center where we checked in.
Okay.
So we parked up there, walked across, checked in, went up, drove back down around here. So that's the way we came from. See, and that's the other parking lot that the guy took me to.
It's like, this
Yeah.
isn't where my car is.
It's a much closer one. See that building right there, this big? Well, I'll let you do whatever your roundabout is going to be before I
I guess
start
the
pointing.
recording's better up here, but might still have to overdub it. So.
Yeah. See that building? That's where Britain works. That's the
one?
computer one. You got
Oh,
this
okay.
small building here leading to this big building right here.
Yeah.
Okay, this is it's like 56, 57, and 5800, I think, if I remember right. That's where the Hall of Flags is in the front there. But yeah, he's in that building somewhere. The time when he finally brought in all of the Eagle Scout stuff, I met him over there.
Alright.
And the next building over is 4500. Medical's there, all the admin stuff is there. Somewhere over there is the graphite reactor, which they do tours of. But I mean, apparently it's a public tour. You start at AMSI and ride a bus or something in. I have to do that one of these days. Because I really don't know how it's set up as far as, if you just come here on your own, whether, you can just show up there and see it, or if they've got specific times. So yeah, right down here, this little building, that's a gas house. That's where the 3 storage tanks are for storing all the SF6 when it's not in the tank itself.
It's quiet in here, sort of. It's quiet in here, sort of.
Yeah, most of the stuff's been shut down.
It's like hissing.
I have a better view of things over here as far as the scale of it. This brass tube, big brass tube here,
Yeah.
that's the ion source. You have a couple of electrodes, you basically draw an arc, inject hydrogen gas into it, and make protons.
My favorite.
Yeah. And then, you know, you have this is a big honking electromagnet. You have
That's a
two-
magnet?
This is the iron from a magnet.
Wow.
See this round thing?
Mhm.
That's the coil, or that's one of the coils.
Wow.
Another one just like it on the other side. I don't know what the field strength is in the machine, but when, you know, I mean, when they were really cranking it up back in the days of doing heavy ions, they'd run about 5,000 amps through these coils. It was strong enough that it would be messing with the CRTs in the control room.
Wow.
This is about a little over 200 tons of iron. So that is how you keep particles going in a circle, is with a magnetic field. But you know, it works later. This is the resonator cabinet for the RF system. Up above, you have the power amp up on top. There's where this big vacuum tube. And a vacuum tube is kind of an old school version of a transistor. This is the big one. It can handle a lot more power than a regular transistor can, and it's more forgiving if you
Wait,
get.
so this is an old school one?
Before there were transistors, there were vacuum tubes.
So what makes transistors better than vacuum tubes?
They are much cheaper to make. Thing is that it's harder to make them handle as much power. I mean, that tube up there is something like 300,000 watts, if I remember right. It's a big tube.
That's where the power comes from, is this over there?
That is actually a couple of motor generator sets for the Iris platform in the next room.
Ah, okay. So unrelated to this at all.
No, it's just a convenient place to put it. But RF is weird in that, I mean, it's, forget everything you know about electronics once you get into RF because it behaves really strange. You can literally have your conductor connected directly to ground and it won't care as long as you're a quarter wavelength away. It's really bizarre. At any rate, this is how you get it going up to speed. You kind of, it keeps cycling as the protons go around.
That's why it's called a cyclotron.
Yeah.
Amazing.
And then you have some elements to nudge it, and then you bring it out the bottom here. This guy is a switching magnet. Because from here, it's a question of where you want to go. Straight ahead, this way takes you to, well, it's not quite straight ahead, it's off a little bit. That takes you to Iris 1. All the way over on the left.
Yeah, that looks like the magnet. From before, or unrelated.
What's that?
The blue and red thing looks like the magnet.
They're magnets, yeah. Magnet. Fine adjust for direction. A magnet to angle you up, and then one to level you out. And that's Iris 2. Now this is another accurate analyzing magnet. This used to be to take the beam into the next room, but they took that stuff out a long time ago. They haven't run there since long before I got here. Now it's just basically used for energy calibration to make sure, okay, this is what we're really running. Well, they don't really run this thing anymore. But this is a cyclotron.
Amazing.
This is a freaking huge cyclotron. I mean, most of these resonant cavities that I've worked with before were the size more like of a refrigerator. Wow. This thing's more like a school bus. The ones I've worked with before, a couple of them were 25 tons, and I think the rest were 50 tons. And this thing's over 200. I remember when Alan first took me on the tour when I started here, he kept saying, how big everything was. The size of the house. This is another type of vacuum pump, though it is a big version of it. This is an oil diffusion pump. What you basically do at the bottom, you have heaters. You boil oil off, send it up the top, and it jets down against the sides where you have the water cooling traces, and it kind of recondenses. So basically, you kind of trap any air molecules in this oil spray, and it kind of brings it down to the bottom, and then you have this yellow piping. It's all part of a roughing and backing network. So you're kind of pumping it out from, the very bottom of it, where it all kind of gets trapped by a layer of spraying oil. This is actually an access door here. I've been in there,
What's it like?
cramped.
Oh,
By the time you're going in there, you're changed over into,
hazmat suits. And
well, sort of, yeah, you've got the changed out of regular clothes into the issued khakis, and then you'll have either a, Tyvek or similar or cloth suit. You can see some of them, like this yellow
so what do they
paper fabric there.
what do they do with them after?
Send them off. Well, after they've had enough time to decay, they send them off to be laundered.
Okay.
A lot of this stuff is just simply being thrown away. But you usually have a separate bag for the reusable stuff. It depends. All of this white stuff here is disposable. It'll either be a Tyvek or a polypropylene, like this guy. It's just it's more substantial than paper.
Like money sort of material?
Not exactly that. It's more of a cotton fiber. Polypropylene, it's plastic.
Oh. I don't think saying it's like paper really.
So, yeah, it's thicker than paper. But yeah, these blue things up here are all flow switches.
Whoa, that's a lot of them.
Because when you're running lots of current through something, if you lose the water cooling to it, bad things can happen in a short period of time. So in addition to, you see all of these tubes right up here?
Yeah, the
All
brass ones or the black ones up
You
there?
got the yellow thing, and then you've
Yeah.
got, okay, that's all the main magnet. You have to pretty much supply individual layers. You can't just put in one big cooling line and do the whole thing. It isn't enough flow to do that, so you kind of supply it pretty much a layer at a time. So you'll have a winding, pretty much kind of goes in, comes back out, and you'll supply that individual winding, and that, that's the only way you can really get enough cooling to the whole thing. But likewise, you can't just, jumper it together, it has to be electrically insulated. So while the voltage on it isn't necessarily phenomenally high, it's still, that's running in basically into a dead short. Seen some before, calculating the, versus voltage and the current going into it, you're running into a third of an ohm. It's nothing. The supply wouldn't know the difference between supplying the magnet or if you just tied the output together. It's a ridiculous amount of current, and it can do a whole lot of damage real quick if something isn't there to take the heat away. And likewise, there's other coils in there for kind of tweaking the beam, and it all needs to be cooled. The RF needs to be cooled. Ion source needs a little bit of cooling, and hydrogen.
Yay.
What this tank is. This thing is set up to run all kinds of things. If you really wanted to, but we don't really want to. And at the end, when we were running, we were just counting protons. I've never seen it do anything but that. Back in the old days, when it was the heavy ion research facility, that big green magnet we saw earlier would direct it in, it would come through the back side and bring it into the center. And you would bring it in at a very low charge state and then have a stripper at the center or some way of ionizing it at the center. So then, I mean, it's your radius of curvature through a magnetic field is going to be much more gentle with a lower charge because it's directly proportional to the charge.
Is it?
Well, or inversely, rather.
Yeah, because it's 1 over R.
Yeah, kind of thinking, yes. So, 0, nothing, 1, a 2 charge state's going to have half the radius of a 1 charge state.
Okay.
So, you bring it in and it's a very low charge state and then you strip it at the center. And that's going back over 20 years since they did that. So, I've only heard it talked about. I've not actually.
Only in legends.
Yes. In the old days. So, but apparently they, at one point, accelerated uranium up to like 1 giga-electron volt.
Sounds fast.
Well, that's a lot of energy there. Okay, so this is the recoil mass spectrometer. Now this is an array, a detector array of high purity germanium detectors. These are newer ones, they're segmented ones that are supposed to be able to tell more about the gammas they're detecting, as far as, like which direction they were coming from. But this has this automatic fill system. See more of those green solenoids up there, like the ones that are on the table.
Okay.
So the computer will, a couple times a day, you'll start to hear an air hiss and it'll start filling them. So, and they have to be kept cold in order to operate. I don't know what what exactly they're using it for these days, but they keep them going. Now this one is one that's kind of here on loan. I think it's an experimental one. Then since we're spraying liquid nitrogen that's ultimately becoming nitrogen gas, there is oxygen monitoring in here. There's actually a lot of oxygen monitoring stuff in the building. Stuff in here is just for the liquid nitrogen. See this little blue thing down there? Should have brought a laser pointer with me. That's there's an O2 sensor sticking out the bottom of it. A little dark gray.
Oh, okay, I see
thing.
it. Oxygen sensor, do not block.
Yeah. So, in the rest of the building, there's some associated with the tandem in case there's a big SF6 leak. Like I said earlier, if you let it all out, it'd cover about 17 acres. Everyone would be talking really, really low until they died. So, at any rate, it gets a little convoluted. We probably ought to come back to that, because most of this, we never went in the East Room, so look at that later.
There's a lot of places.
Yeah, but here, this is the crazy one, because you got a lot of beam pipe to get from the tandem to here. Luckily, all this stuff is the experimenter's problem. But you've got, aside from quadrupoles, bending magnet, let's see, I think, these are, you've got a quadrupole, and you actually have what's called a sextupole, which is a 6-pole version, which they tell me can do something with the shape of the beam. I don't claim to understand it. Well, quadruples, vacuum pumps, stuff.
And
then
there's Huxtables.
Huh?
There's Huxtables. They make good sitcoms. That's a
Yeah.
joke. There are no such thing as good sitcoms.
We have these big electrostatic deflectors. At this point, what you have coming down here is no longer directly the beam. You'll have run into something down there and knocked something else entirely loose. Usually, as I understand it anyway, but I guess you could bring the original beam down. We'd have to talk to researchers about that. But yeah, the idea being that with enough odd bends and things, you can filter out everything that isn't what you want. So you get down to the end of it all, and you only have that specific isotope with that specific energy that you're looking for. So it's kind of stripped down now, but there used to be another detector array here at the end and a little, target station.
Am I allowed to
Tape
be
drive.
on these steps?
Sure.
So many cables still.
Oh, yeah, well, you want to see, I mean, I'll show you the big Insanity cable bundle down here. Walk past it. But yeah, you got cable. These cabinets here. Hello. She's gone. Good. I used to see pictures of this back some years ago. Flip on its blinds, but these old sodium mercury, whatever the hell, it takes them a while to warm up.
I think even in the dark, it's fairly
Yeah.
light.
I think I have pictures of this anyway. But it's such a tangled mess. We're talking to one of the researchers, and he's like, I know exactly what all of those are. That's another. Yeah. This is Iris 2. Now,
What is it?
you run in the back there. I don't know how much you can see it, but there's a line that comes in. A beam line, like there's a
Somewhat, yeah.
red magnet back there.
Okay, yeah.
That beam line comes in. That would be protons from Oric. Now, what this normally you did, this is you have a uranium carbide target in there, and when beam hits that, you get some fission. You create a whole bunch of isotopes of a lot of different things, and you extract out the specific one you want, or at least a specific mass. You have this red thing here. This is BAM,
Yeah.
beam analyzing magnet. IR1A, IR1B is the other part. Between these two, these are going to filter out down to a specific mass coming out of it. And then you're going to send that off to the TAM.
Okay.
So, I think I can't remember where no, I guess we haven't gone into the East Room. Alrighty. Because that's where that goes next from here. I mean, likewise, you can also just send it straight upstairs. There's a little research station there. That's what this magnet is. I don't know that I've ever seen anyone do anything with that. See this odd collection of hoops
Yeah.
around that? Okay, that is some of the, voltage divider network stuff. The white in there in the center is ceramic, and then you've got little metal sections, ceramic sections.
Oh, so it's just like the tandem itself.
That's a short section because this platform, when it's running, is operating at about 200,000 volts.
Okay.
So you have to have, the insulators, and then usually somewhere in there is a, some resistor voltage divider thing. bit. This is to kind of give you the initial energy to get going.
Okay.
So it's either you start grounded and accelerate it up, but then okay, now you're on, on a working to a high voltage platform, where you start here and push it off with the voltage, and then you've got beam going, and you're at regular ground potential, and you can take it where you need to. The challenge, though, is this has to be pretty much self-contained. But this section of pipe here is a transition from a high voltage down to no voltage. There's another one, on the far end where it comes out, and heads off to the tandem. Can't really see it from here. And then where the beam comes in from Oric, there's one of these sections as well. You just need something to insulate it, and that's just a simpler approach than trying to make a big ceramic insulating tube. So, at any rate, though, any questions off the top of your head on that?
So the tandem is the main show of everything here.
Kinda, yeah. When you go from Oric, which makes protons, you hit an Iris platform target. It's called a target ion source. Generate isotopes, extract the specific isotope you want, and send that into the tandem. And then from the tandem, that goes to some experiment end station. Either they're wanting to do what's called an implantation, where they're basically just collecting enough of it in something, or they're actually trying to force a reaction. We're going to run this into this and see what it makes. It should make this. Like at one point they were, I think, bombarding, I'd have to look, maybe like aluminum with titanium or something, trying to make uranium. I don't know what the merits of doing that are, but apparently someone felt that it was important to do. Now, it gets very hot right there where the beam's hitting, particularly if you're causing fission there. That's more radiation on its own, in addition to, just hitting it with basically about, I think it was around, 50 to 70 MeV protons. They hit at maybe 15 microamps of beam, which in terms of other machines I've seen isn't much, but here it's a lot. So electronics does not survive well in high radiation. It just kills it. So the electronics tends to be remotely located, which is a challenge when you're trying to have it at high voltage. So we have another room next door. And likewise, the other Iris platform, it was the same story. Well, someone is trying to do something. All of the electronics are here. So from there, what you have is a few optical interfaces to get info off of here. But yeah, here's a voltage divider and power supply.
The yellow kind of
All
thing
those
there.
little cylinder things. That's part of a high voltage supply for the 200 kV, because this platform is at the same potential as the one in the next room. So the electronics that are on here, you can't take any regular kind of sensors or controls or anything, have them at ground potential, and then connect it into a high voltage system. It'll fry everything. So everything on here, all of the power supplies for any magnets, block pole steering, any of the high voltage supplies for electrostatic stuff, it all has to be on here. So it's at the same potential. Now, in order to get power to that. You saw in Oric Bunker there was those 2 motor generator sets. Okay, you have a similar setup here. These are just outside though. You have motors outside, you have generators here on this platform. And you have a big non-conducting shaft. So that way, again, you can't just run an extension cord and throw it onto a 200,000 volt platform. It won't work. But you can run a non-conducting shaft across and just generate the voltage on the platform itself. So that way, everything in here has power. You know, and the means of bringing it in is mechanical. It's insulated.
Okay.
This is more experiment station. There is a small scale version where they kind of test, you know, small versions of a target ion source. That's in the other room, online test facility. And then they just kind of test extraction and analyzing and everything in here. Whereas, you know, the Oric's delivering, you know, 10 or 15 microamps. The Tandem is limited to like 50 picoamps on protons, just because it just gets too radioactive to run any higher. So it's a very small scale, let's see if this works kind of thing. So this is where they, you know, bring the beam through and see if they've accomplished anything. Here's the one detector that I wind up filling every week. It's over here. These are target ion sources. So you actually, you know, run protons into them. Don't ask me where everything goes in or out of. I do not know. But you run protons in there. There's uranium carbide in it. It's not full of uranium carbide. And then, you know, you extract out the actual isotope fission product that you're after. Actual online test facility is what this is. So this beam line coming in here, that's where, I'm getting myself all mixed up here. Yeah, that's where the protons will come from the Tandem. So this is just kind of a small scale version. So it's going to come in and hit that way, and then you're going to send whatever off that way at a right angle, extract it from it. Other than that, this room can get a little bit toasty. You really need to go in it. Would be into that where the Iris 2 platform was. The beam line runs through that room, and it splits off. These two lines join together there, and you can decide whether you're sending it off to RMS or to OLTF. There she is again. Magnets. Oh, vacuum pumps, more quantum holes. Magnets. They're
Quadruples.
no, we saw what we needed. Yeah. You have to run things at high voltage in there. They've got their own safety systems. They're hoping to do some runs into here soon.
Hey, it's working now.
Okay.
It's on now. It's working. Something.
Well, the fan's there.
Fan's working.
And it's important. Particularly auric into the target ion source, and then, it's a matter of separating out the isotopes. And this pretty much whole thing is supposed to be representing, well, I guess through here, the actual IRIS platform. It used to be called RIB injector, radioactive ion beam. And then there's a big isobar separator, just to separate out that one specific isotope they're after, then into the tandem, and then off to the experiment. You see a map of the building. Some of this stuff will start making a little more sense as to why it's so convoluted. Other things just get more confusing. Oh, here's a map. Well, it didn't really show the beam lines. But let's see now. This is RMS, that big room. This is that little, the room she just closed the door to. That's
Okay.
right here. This room, this is the room we were in that had that yellow pole across it with the
Okay.
IRIS platform. So that beam line was going, those two were going into here, going across there. This is the east experiment room. We're about to go in here. And then it kind of bends around, and then here's the tandem. So this is auric. So beam from auric would be coming, and this is the IRIS 1, the actual platform, and then the electronics platform. So beam would come out of auric, either go into here or around into here to the IRIS platform. We'll go IRIS 2. From there, it's kind of looping around, and then kind of, coming through this wall, joining with another beam line, and then going into the tandem. Now, for the online test facility, you're starting pretty much at the stable injector, which is second floor, not shown here, but it's pretty much right over here. Up into the tandem, you're coming out, going through beam line that's through here, bends over here, goes through here, splits off here, through here, into that, and then you have it kind of coming through this little closet room, and then out into that room where Yuan was sitting at her computer there.
Okay.
So it's there are some drawings somewhere that have all of the beam lines shown.
But no one understands them.
Yeah. It's very confusing trying to get your bearings from that standpoint. Where we're going now is that door right there.
With the 3 on it?
Yeah, that one. Kind of stuck. Now the tandem is that way. So a beam would come through here. Head off. The next room is IRIS 2. Goes through IRIS 2, and from there it's either going to go to the online test facility or into the RMS. This other stuff really doesn't get used anymore. This guy, I don't know. Never seen it used. All the Angie EMGE, but I don't know what it's supposed to do. You've got various things.
Things.
Oh, here we go. So, a lot of this, mass spectroscopy is basically figuring out what you have just based on how it's curving in a magnetic field. So, from that standpoint, lots of magnets get used. You can see this one up close. Now this was actually a new line that they put in a couple years ago, but I don't think they ever had a chance to use it before they shut everything down.
That's a shame.
I think they're going to move it to somewhere else. That's just kind of the state of things. Oh yes. The big Isobar separation between analyzing magnet and this big blue sucker. If you can't separate it with that, it can't be separated.
Huh. So what, strongest magnets in the world?
It's not a matter of that it's strong so much as that it's so long and very precise, accurate and all that nonsense. So that by the time, even a subtle, I don't know how much you ever studied it in physics. If you put together a bunch of protons and neutrons into an atom, they weigh less.
Yeah, because
Okay,
the
than
energy.
some of their parts. If you change the number of protons and neutrons, that mass changes subtly. This guy, they tell me, can tell the difference. They can split them out based on that little difference in mass. So if you're just sending through, something of some given atomic mass, you can set it different for, this mass of what isotope. It can separate out that little bit of mass. 2 stages to do that, but
Crazy.
at any rate, what else is really much else to show.